In this video, we're going to begin to talk about Chapter 2 in representing motion. And to start with that, we're going to look at Section 1, Picturing Motion. And the main idea of Section 1 is that you can use motion diagrams to show how an object's position changes over time. The two essential questions that we're going to answer is, one, how do motion diagrams represent motion? And two, how can you use a particle model to represent a moving object? Few vocabulary terms that you're going to hear are motion diagrams and particle model that may be a little new for you. So first off, let's talk about motion in general. And when an object is in motion, we notice that there is a change in position, or its position changes. And so that's what motion is by definition. And its position can change in many ways. One, it can move in a linear path, it can move in a circle, or we can have this back and forth vibration, or what we call periodic motion or oscillatory motion. And so those are three basic ways that a particle can move. A description of the motion relates to both the place and the time, the position of the object and the time in which it occupies that space. So I want you to think and even possibly list and describe a few examples of motion from your own experience. What have you seen just today that has been in motion? So think about that, jot it down, we'll talk about it in class. So motion diagrams show an object in motion, and they do this by having several snapshots. So think of maybe a flip book or a picture that is taken over and over again, but the only thing that's moving is a person that's walking across a landscape. And so a series of images showing the position of moving objects at equal time intervals. That's the important part. Equal time intervals, we call this a motion diagram. So if we were to say that these 5 diagrams of the stick figure were a motion diagram, then this was just a snapshot taken of the same person at 5 different time intervals. Now we could replace this model, and instead of having a stick figure that we'd have to redraw, or a person or a car or whatever it may be, we could replace the object in question with a dot, or what we call a particle model. And so a particle model, you just replace the object of interest with single points. And this allows us to better see what's happening with the object. We're not distracted by the ponytail or the fist that this stick figure is making. We're just looking at the dots. And so what can we conclude from these dots? And we're going to work on that a little more in class. But one thing we can see from these dots is that the space in between them is the same from one time interval to the next. And so you may ask, well, what's the conclusion that we can make there? Well, we're covering the same distance in the same amount of time. So think about, what does that mean? So this section is a quick one, and so hopefully you can answer these two questions. How do motion diagrams represent motion? Well, they're just snapshots that show us an object that is moving at equal time intervals, and we can use a particle model to replace that moving object with a dot, and so we can examine the space between those dots. Now we're going to do that a little further in class and later in the video. So moving on into section 2, the where and the when, this is the real meat of it. And the main idea here is that a coordinate system is helpful when you are describing motion. Or in other words, when you think of coordinate system, think of, we need a reference point. We need something to measure from, like an origin. So we have a few essential questions here. We want to know, first off, what is a coordinate system? How does the chosen coordinate system affect the sign of the object's position? How are time intervals measured? What is displacement? This is a very key term here. How are motion diagrams helpful in answering questions about an object's position or displacement? So notice the motion diagrams are coming back into play. Some new vocabulary that you may have not seen before or just can't quite remember what it means is over here on the right. We've got coordinate system, origin, position, distance, magnitude, vector, scalar, time interval, displacement, and resultant. We're going to talk about what all of those are and how they factor into motion. So let's talk about a coordinate system first. What is a coordinate system? And a coordinate system tells you the location of the 0 point of a variable you are studying and the direction. So this is important. It's the 0 point and it tells you the direction in which the values of the variable increases. So the origin is basically just our starting point. So in this diagram here, we have a nice wintry landscape, and the origin is just some point over here on the left. And that's where our variable in question, which we call x in this case, has a value of 0. So the variable has a value of 0 there, and we know it increases moving to the right because that's how this coordinate system is oriented. So let's consider a runner on this coordinate system, and you can indicate how far away the object is from the origin at a particular time by drawing an arrow. So let's say this runner is represented by these dots, these series of dots. So we have a particle diagram here, and we can look at any time interval. So from the first dot to the second dot, we can represent the distance that the runner covered by this arrow, and it's this green arrow right here. And the position that we talk about is the distance and the direction from the origin to the object. So that green arrow is the position. Whereas if we look at another point in time, this end point, we have another position arrow. So notice that these arrows are different in length, but they're both pointing in the same direction. So those two quantities are important when we're talking about position, both the length and the direction that it's going. This brings us to the idea of vectors and scalars. And so when we talk about vectors and scalars, we say that quantities have both size and direction. The size we call magnitude, and the direction is going to tell us, well, is it right, left, up, down, north, south, east, west, maybe at an angle. That direction, when it's coupled with a magnitude, gives us a vector. Vectors have both magnitude and direction. And vectors can be represented by arrows. So the position here that we just talked about, those are position vectors. x1 is a vector and x2 is a vector. The difference between these two is x2 is a lot longer than x1 because there are two different positions. The position out here at 30 and the position here at 5. However, a quantity that is just a number without a direction is called a scalar. Examples of this would be time, distance, and temperature. When you ask what time is it, we say it's 3 o'clock or it's 12:13. We don't give you a direction on the time. We know time is always moving forward. Same thing with temperature. You just give a reading on the thermometer, just like you do distance. Now, not to get confused with distance and position, remember the position we just discussed had a direction with it. Now, I want you to think about this question here. Is mass a scalar? So think about what is mass, and is that a scalar or a vector quantity? So mass is, in fact, a scalar quantity because it has magnitude, but it has no direction. So the difference between two times is called a time interval, and we're going to refer to it as a time interval a lot. And we're going to use this Greek symbol, delta, to represent a change in time. And to find the change in time, say we want to find the change in time from this position here and this position here. Well, we take the final time minus the initial time, and that gives us the change in time. And we call this the time interval. A change in position is called displacement. So when we're talking about the position from this spot here to this spot here, that change in position is the displacement. And so this runner is at 5 meters at one point in time, and then at 25 meters another point in time. Well, how far did they move? Well, we once again use the final minus the initial. And so the change in the position of that runner gives us the displacement. And we also represent that with a delta x, delta meaning change. A vector that represents the sum of two other vectors is called a resultant. So we might have a person that starts at the origin and moves 5 kilometers east, but then moves another 2 kilometers east, and we want to find, well, what is the result of those two movements? That's why it's called the resultant. That resultant is 7 kilometers east, and we get that by adding the two magnitudes together. Why can we add the two magnitudes together? Because they are in the same direction. However, if this person moves 4 kilometers east, but then decides to turn around and move 6 kilometers west, well, those are in opposite directions now. We have east and west, opposite directions, so the resultant is not adding 4 and 6 together to get 10, but instead subtracting 6 from 4, because we're saying 4 is to the right, to the left is negative, and we get 2 kilometers to the west. So that means that the result, where this person ends up, who started at the origin and moved 4 kilometers east, but then moved 6 kilometers west, is really, in the end, just 2 kilometers west of the origin. Another example here is if you're at the origin and you move 7 kilometers east of the origin, and then you decide to move 4 kilometers west, well, 7 minus 4 gives us 3. That's a positive 3, so that means we're still to the east of the origin. So the resultant is 3 kilometers east. Notice it has both a magnitude and a direction. So hopefully from this video you are able to answer these essential questions and give a brief definition of these vocabulary terms. If you have any additional questions, come to class with those questions tomorrow.